Hello. If you are interested in analyzing variations in your local climate, today I will be showing how to develop analyses based on greenhouse gas levels, namely carbon dioxide, methane, and nitrous oxide, and how often increases or decreases in each of those are associated with increases or decreases in temperature. This is especially useful in developing a more nuanced understanding of predictive analyses that climatologists use, as well as private risk analyses, say you're home searching or in corporate contexts, developing a more nuanced cost-benefit analysis of climate-dependent supply chains. The data that we will be using is collected from NOAA's ice cap data from the poles. However, you are able to use your own readings from thermometers or other climate-based paraphernalia. Our current set of observations is a given year, the methane and nitrous oxide levels for that year, as well as a temperature reading of how different that year was in comparison to today's temperatures in degrees Celsius. The main value add of a regression analysis is to have a machine identify patterns and correlations between variables that you might be interested in. Since we are trying to identify all of the effects that time, CH4, and N2O have on temperature, we will want to isolate each of those variables into a data structure for reference later on. This data structure will simply be an array with the corresponding categories of data that we will be identifying as independent variables to act on our dependent variable listed out here. And now that we have identified those variables, we are able to start training the regression. To do this, we will be implementing the linear model function. The pros of this type of regression analysis are that each coefficient that we will receive via this method will be, in essence, a slope. So we will be able to say the associated increase in temperature by one increase in parts per million of CH4 is X. We will be using the linear regression functionality here, which is a predefined set of instructions that will allow the computer to train on a set of data. And since we already have the variables identified, we will just need to fit this linear regression onto our data. So how that is done is we simply define all of the independent variables here, and we define the expected outcome variable here. To then access each individual correlation coefficient, we will need a for loop that will run through all of the coefficients that have been generated by the trained regression and output them alongside the corresponding independent variable name, so that we're able to see for each individual independent variable listed up here what the expected coefficient might be, or for an individual change or increase in in the individual variable levels, what the associated increase is in the ultimate outcome. All that is left to do is run the code. And you should see that we have an output of each individual independent variable here, CH4 and N2O, along with the associated slope. For each part per million increase in CH4, we expect a 0.001 degree increase in temperature. These numbers give us a measure of how often temperature moves when each individual independent variable moves. Climatologists use this research to better understand what impacts climate by developing a prediction based off of the already identified independent variables and then measuring how deviant the reality is from their expectation. To create a sophisticated predictive analysis, we at USA Facts have crafted a data set in which we analyze how different temperature and precipitation readings are each given month to 20th century averages. Using this data in predictive analyses will allow us to not only analyze the strength of association between individual independent variables and temperature readings, but also the acceleration in changes in temperature and precipitation over time. All data are linked below. Thanks for watching.